students, welcome back to my YouTube channel. This is Kashima Soni and today we are going to start a new chapter, that is carboxylic acid derivatives. So let's proceed to the further slide to see what we are going to take up in this particular series of carboxylic acid derivatives. Let's see. Okay, so the topics that we are going to cover in the first part of this chapter would be introduction, electronic structure of acid derivatives, and nucleophilic acyl substitution. And in rest of the two videos, we'll be taking these topics separately. That is your relative stability of acid derivative and their order of reactivity. And next would be your acid catalysis of nucleophilic acyl substitution. Correct. So let's proceed further to the introduction of this particular topic. All right. So certain classes of your organic compounds such as acid halides, acid anhydrides, esters and amides, which are obtained by the replacement of OH part of your carboxylic group, carboxylic acid, by X, any of the halogen atom, by OCOR, by OR dash and by NH2 respectively, they are going to be known as the functional derivatives of carboxylic acid. Correct? What they are known as? Functional derivatives of carboxylic acid, or you can simply call it as derivatives of carboxylic acid, and which on hydrolysis will be going to give you your parent acid, that is carboxylic acid, back. Correct? So this is your structure of carboxylic acid, and there you can see on replacement of OH with any of the halide group, you are going to get acid halide, and the structure of acid halide is as shown over here. And if you remove the OH with OCOR dash group, you are going to get acid anhydride. You can see that structure. Correct. And when you will be removing OH with your OR dash, it is okay. Then you are going to get RCOOR, that is your ester. Correct. This is your another functional derivative of carboxylic acid. And here comes the another part where you will be replacing the OH part with NH2, and you are going to get this structure, that is amide, or you can call it as acid amide. Correct. So where R and where R and R dash may be different or simple or substituted alkyl or aryl group. Correct. So I hope that is quite understandable to all of you. Proceeding further to the electronic structure of acid derivative. See, you can see the general electronic structure of the acid derivative, where your L could be anything. It could be OR dash, it could be OCO OR dash. Okay, then it could be your any of the halide atom, it could be NH2. Alright, so the carbonyl carbon which is attached to the oxygen atom like this by double bond, add two monovalent group, that is R and L. Monovalent, that means they are going to have a valency 1. Okay, so which is what your monovalent groups. Okay, then further this carbonyl carbon, like the carbon atom in carboxylic acid, it is going to be sp2 hybridized. Okay, then comes the part of the molecule immediately surrounding the carbonyl carbon. It is going to be flat as the angle RCL and LCO, angle RCO, they all are 120 degree. Correct. So the structure that is going to look like, let me draw it over here for you for better understanding. Okay. All right. So you can see the structure of your carbonyl, acid derivative of carboxylic acid. Okay, where you are going to see the complete delocalization of electrons over here. See, these are the orbitals of your carbon, then oxygen, and yes, you are going to draw the orbital of L as well. And let me redraw it first again. Okay. Alright. So, by drawing the structure like this, you are trying to show that the electron are completely delocalized over here. Correct. This is what you are trying to show over here. I hope it is quite visible. If it is not, let me change the color of the pen. Okay. Alright. So something like this you are going to see. So what is happening? The group L, it could be anything like Cl as in acid chloride, O as in anhydride, correct? N as in amide. They are directly linked to this carbonyl carbon, correct? And what is happening over here? It has at least one lone pair of electron in its in its p orbital. Okay. Then what is happening? This p orbital on group L may also overlap with p orbital on carbon, as you can see, and oxygen. Correct. So what is happening over here? It is basically showing the pi bonding between your carbonyl carbon oxygen and atom of the group L. So what is happening? There is occurring complete delocalization of electron over here. Correct. So that is about the electronic structure of acid derivative. I hope you have understood that well. Let's proceed to the another important topic in this series, that is okay, this we have already discussed. That further, the group L directly linked to the carbonyl carbon has at least one lone pair of electron in p orbital. This p orbital on group L, it may overlap with the p orbital on carbon, oxygen. These all are the things that I've told you in the previous slide. So proceeding to the further important topic, that is our nucleophilic acyl substitution. Alright, so the most common feature to all of these acid derivatives in the nucleophilic substitution reaction is that all of these groups, that is chloride, OCOR dash, OR dash, NH2, they all are replaced by some other nucleophile or some other basic group, correct? So that is one thing. Okay, but you should know what is nucleophilic acyl substitution. Okay, so you can see this particular group over here. Okay, this is your acyl group. This is your acyl group. Okay, and over this place, after the removal of this any of the group present next to the acyl group, after the removal or the expulsion of this group, your substitution of nucleophile will result in the overall nucleophilic acyl substitution reaction. I hope that is quite understandable. This term is quite understandable. Okay, getting that? So that is one thing, that on your next to your acyl group, your nucleophile is getting substituted. That is all about nucleophilic acyl substitution. Okay, all right. So proceeding further, nucleophile, you can see, is going to attack this electrophilic carbon. Now you will say, how this is going to be electrophilic carbon? See, oxygen being more electronegative than your carbon is going to attract the shared pair of electron towards itself, correct? And which by which your carbon is going to be left with partial positive charge, which makes it susceptible to the attack via your nucleophile, correct? So nucleophile will attack to this carbon, and it will form this tetrahedral intermediate like this. Alright, so this lone pair of electron, or this negative charge on carbon, on oxygen atom will will shift its electron density back to this bond when your another group present is going to leave your molecule. You're going to leave your tetrahedral intermediate as such, and it is resulting into the formation of this nucleophilic acyl substituted product. Correct. So that is one thing that I have given you a summarized portion of it. Let's see how you are going to attempt it if it is asked in your paper. Okay. So this is the reaction where your nucleophile is attacking your electrophilic carbon, and it is resulting in this this product. Okay, where your group L has been linked with the pair of electrons, with complete pair of electrons like that. You can see in the previous slide. Okay, you can see over here your X group, and over there it was L. Over here I have taken it as L. Okay, and it will be leaving with this complete pair of electron. This from this bond, it is taking the complete pair of electron, and also carrying the negative charge along with it. Okay, so since this mechanism occurs at acyl group, it is thereby referred to as nucleophilic acyl substitution, that I have also told you. Alright, so proceeding to the mechanism, what is going to happen? Basically, this mechanism is two-step addition elimination mechanism. Okay, what is going to happen? Your nucleophile is going to attack your electrophilic carbon like that, and this bond will shift its electron density to the oxygen, correct? Because your oxygen is more electronegative. That is one thing. All right, so what will happen? It will give you this tetrahedral intermediate. Okay, this tetrahedral intermediate, and that is the process. That is your first part, that is addition. Proceeding to the next part, where what will happen is that this lone pair of electron will be shifted back to this bond, and this group will leave. Being a good leaving group, it should be leaving it first, and then it is going to result in this particular product and this L negative, correct? So that is your addition elimination. All right, so as in like in aldehyde and ketone, the carbonyl group present in acid derivative, it is highly susceptible to nucleophile attack. So it is mainly due to the addition of your oxygen atom to accommodate the negative charge. That is one thing. Therefore, it is reasonable to assume that step 1 is similar to the addition of nucleophiles to aldehyde and ketone. Kind of similar to that of step of your nucleophilic addition to aldehyde and ketone. During this addition, your trigonal carbon, it is going to get converted to tetrahedral carbon. In the intermediate, you can see this is your trigonal carbon over here, and this is now your tetrahedral carbon. Okay, this carbon we are talking about. Alright, so proceeding to next slide. Okay, so there are some more concepts related to nucleophilic acyl substitution reaction, which I hope you may love to learn. So proceeding further. So the formation of tetrahedral intermediate, it should be susceptible to steric hindrance. What they mean, if the bulky group are present around the carbonyl group, it is going to be lesser susceptible to the nucleophilic attack, correct? So your आपकी जो न्यूक्लियोफिलिक असाइल सब्स्टिट्यूशन रिएक्शन है वो प्रॉपर्ली प्रोसीड नहीं कर पाएगी उस केस में, अगर आपके पास जो R है वो बल्कि ग्रुप होगा. तो दैट इज वन स्टेप. ओके, फर्दर इट शुड बी रिटार्टेड बाय योर electron donating substituents, correct? So which means your electron withdrawing substituent as in R group will be promoting your nucleophilic acyl substitution reaction, correct? Okay, what is the reason behind that? Because your electron withdrawing substituent will be going to disperse the negative charge in the intermediate. Okay, so this is the reason behind that, and whereas your electron donating group is going to intensify the negative charge, correct? So that is one reason. Okay, and in your second step, the reorganization of electron occurring, it leads to the formation of substitution product. That is also one thing. Okay. Alright, so another important part is the ease with which the L group is expelled. It completely depends upon the basicity. Correct. Weaker the base, better is the leaving group. Remember this point, weaker the base, better is the leaving group. Okay, so in your nucleophilic acyl substitution of all of these functional derivatives, what will happen? Your Cl being a weaker base, it is going to be a good leaving group. Okay, so Cl is going to be your good leaving group, and then comes your OCOR dash, then comes your OR dash, then comes your NH2. So which one is your good leaving group? This one. This one is going to be your good leaving group. The reason is that it is going to be less basic in nature. It is your basically weak base. Okay, which is why it is going to be good leaving group. Okay, so that is one thing. Proceeding further, in contrast, if the aldehyde and ketone were to undergo nucleophilic acyl substitution reaction, it will basically be involving the removal of your hydride ion or the alkyd ion, like this. You can write like this on the superscript. Okay, so since these are the strongest bases known, therefore aldehyde and ketone do not undergo nucleophilic substitution reaction. So question like that could be asked, why your aldehyde and ketone do not undergo nucleophilic substitution reaction? So the reason is, one reason is quite clear, that it is going to involve the removal of hydride ion and alkyd ion, and these two are basically very poor leaving group. So if they are going to be poor leaving group, how they are going to get removed in the reaction, and how it is going to facilitate your nucleophilic acyl substitution. Okay, so this is the one reason. So this is how you can see the mechanism of the same, where nucleophile is attacking your electrophilic carbon, and the structure tetrahedral intermediate is formed like that. But this is not proceeding further. Why? Because both of these are poorest leaving group, correct? Which is why your aldehyde and ketone do not undergo nucleophilic acyl substitution reaction. Okay, and this is a complete overall mechanism for nucleophilic acyl substitution of your acid derivatives, correct? So okay, by this structure what they are trying to explain is that your overall structure, if it is since you can say, if it has not lost its double bond, if it is if a partial double bond is still present over here, so what they are trying to say is that this complete structure is overall negative, carrying negative charge. Okay, this is what they are trying to say. So yeah, that's all about it. I hope you have understood that well. So if you have any kind of queries, you can ask in the description box, and I hope you have understood it well. And keep sharing, keep liking, and keep showering your love. Thank you.